So it says a parallel plate capacitor consists of two conducting plates separated by a distance d as shown above. The plates may be considered very large so that the effects of the edges may be ignored. The two plates have an equal but opposite surface charge per unit area. The charge on either plate resides entirely on the inner surface facing the opposite plate. Now, there's a lot to take in with that discussion, isn't there? So, first, if the top, I think they told us the top one is the positive and the bottom one is negative. And they say, and I want to read this carefully, the charge on either plate resides entirely on the inner surface facing the opposite plate. Now, I think that makes some amount of reasonable sense considering the plates influence each other. Would you guys agree with that? Now, something that you may not have put together, and I think you should. Let's look at the electric field from the, consider just the top plate for a minute. Electric field, something like that. Except not really, right? Because we know things, right? We know things. For example, there's a plate there. So we know that the electric field would be better, I guess, if I drew it like this. And then like that. Because it won't exist inside the other plate because it's a conductor. I know that I might be able to sense it on the other side of the plate, but right now that has to be true, correct? Any question about that? I'm looking at you. Please speak.
Okay. Why isn't the arrow at below the negative plate pointing towards the negative plate? It's a negative charge.
I'm talking about the positive plate only right now. I promise to color code it so you can figure it out.
Okay.
Here, I'll help you out, just because, you know. But when I go to the other plate, I'm going to make that one a different color. And I'll stick with the red, white, and blue. Today is, homecoming day.
America.
I'm trying to, America Monday, okay?
Yeah.
Excellent.
We love America.
Okay. This as well. Do you understand why I drew it there? Any question about it? All right, so we're all good so far, right? All right. We are told, and I want to pay attention to this, that the charge resides on the inside edge of the plate. I'm not going to zoom in and try and make this perfect, but you get the idea that the charge has been pulled here because, and I think this is not unreasonable, there's a negative charge on the other plate and the charges attract each other. So down here, negative charges. But we know that the top plate has an unbalanced charge and is balanced positive, and the bottom plate has unbalanced charge and is unbalanced negative, right? Because they say that, right? The top plate is positively charged and the bottom plate is negatively charged. Now, as Owen was trying to encourage us to consider, the bottom plate also is creating an electric field. But remember, electric fields originate at positive and terminate at negative. So there will be this, correct? Due to the negative plate. And then, clearly, if I continue on with that idea, there's going to be this and this. We good so far? Miga? These are not forces, these are electric fields. No, it said for us just to talk about what's between the two plates. That doesn't mean that that's what I have to talk about. I can talk about whatever I want because I'm a teacher. Is that all right? Now, in trying to answer your question maybe more thoroughly, if I took this plate away, you would agree that there would be not the red arrows, but the blue arrows for sure without the gap, correct? Is that yes or no? Okay. And you agree from last week that we talked about the fact that just having a piece of metal there doesn't prevent the electric field from continuing past the metal. Right? We saw that last week. When we had a charge inside a conducting sphere, the electric field was still sensed outside because of Gauss's law. Same would be true here. So putting this plate here doesn't prevent the electric field from existing in the space that we just talked about. It just won't exist where the conductor is. But I want to emphasize this, and I'll wait for just a minute. I think it would be true to say there is no electric field outside the plates. That's what I'm trying to impress upon you, is that the fact that there's a positive and negative plate creates electric fields that cancel out on the outside of the two plates. That's why we're focusing on the inside. Do you understand why I went through this now? To show that there is no electric field outside the plates, but not because the electric field couldn't extend there, but because the other plate negates it. So having the two plates there concentrates the electric field between the plates and wipes out the electric field outside the plates. So there is essentially a self-shielding mechanism in place here. Everybody good? All right. So the next says, by applying Gauss's law to the rectangular box whose upper surface lies entirely within the top conducting plate, as shown in the following diagram, determine the magnitude of the electric field E in the region between the plates. There's some extraneous information here. Hopefully you picked out that although they gave you this value for D, you didn't need it. Now, if you had question C here, you would have needed it, but we didn't have question C. So let's take a look at a Gaussian surface. I'm going to use a box. I'm not going to try and draw it 3D. I don't think I need to. Our Gaussian surface, is it all good? Now, we did this before, but they are forcing us to use this Gaussian surface, correct? All right. No big. I think we could still work this out. I think there's only flux through one side of this Gaussian surface, the bottom. Right? Because one part of the Gaussian surface is inside the metal, we know there's no electric field there, so there's no electric flux there. So this side, no flux. This side, no flux. And this side, no flux. We all good with that? Now there's two other sides, I'm not counting, the front and back of our slab or our cube, but there'd also be no flux in those either, right? Because of the symmetry here. So the only flux is through this surface. I don't know what the area of that surface is, and it doesn't matter, does it? So I'm going to say that the flux through that surface is going to be equal to E dot dA, and this will be the net flux for the whole cube. And it's just going to equal E times the area of the top or bottom. I'm going to do the same thing for Q enclosed. Now Q enclosed, that's going to be, they drew it on the positive plate. So I'm going to have the positive sigma, but they're the same, just opposite sides, times A. That has to be Q enclosed, because it's enclosing a portion of that positive charge, and the amount is dependent on the area of that box. Is everybody all good with that? So Gauss's law, Q enclosed equals epsilon naught times the flux. And we get an answer that I think is somewhat expected. Plugging in what I have, solve this for electric field, area cancels out. Now, this is not the electric field next to a infinite sheet. You notice the difference, right? This is the electric field between the plates. The electric field next to an infinite sheet is half of this. Does it make sense? The electric field in between the plates is doubled. Right? There's two plates contributing to the electric field. I would not be surprised that it effectively doubles the field. So are you not surprised by that? Are you clearly seeing me point this out to you so that you will remember this? I'm not pointing this out arbitrarily. I'm pointing it out because this is important. The electric field between the plates of a capacitor like this, two charged plates, would effectively double the electric field. Even though when we did all of this, it felt like we had less field because there's no field out here, and we counted that field when we did the infinite sheet. The fact that that field is missing apparently contributes to us figuring out that it doubled the field. Notice, we didn't have to enclose the charge for the bottom plate in order to get this doubling effect. The math worked out anyways. So I want to point this out to you that this is not a feature. This is part of the way it's supposed to work. Yeah. Worth recording because what if you guys didn't hear what he asked is if we had taken the box and I can't take just the box. Let me just draw a new box to make this quick. If I had done this box, Gauss's law is still preserved, right? I would have enclosed no charge. But I also couldn't use this to figure out the field between the plates because there's no surface between the plates. The reason I bring this up is there's been maybe a dozen example questions over the last 40 years. So that's, a lot maybe, if it's a dozen over 40 years. So maybe it happens every couple of years you get one of these questions where you have to draw in the Gaussian surface on a diagram they give you. And they'll have a point of why you're drawing in. Like they might say, drawing a Gaussian surface that could be used to determine the electric field between the plates. And they're specifically looking for people to draw in this surface. This surface obeys Gauss's law. It has to. The law is not going to be a problem. The problem is that that box can't be used to figure out the electric field between the plates because there's no surface between the plates. So if you're asked to draw on a Gaussian surface, not every Gaussian surface is okay to draw. What's funny is that you could draw this Gaussian surface and it'd be fine. You'd make a reasonable argument, I hope, that there is no field here because of the way they cancel out. But this field would, this box would work. However, I would encourage you to consider that if you have a system, and this is a good example, where they tell you it's a conductor and they tell you where the charges are on the conductor, maybe place one of your surfaces inside the conductor. That guarantees a zero, right? And guaranteeing a zero on having to do your Gaussian law is always, always better for you. So when you can, I would definitely put a surface inside your conductor when possible. Record just for posterity. We're trying to understand a question posed to us by a student. Those of you who watch, there's not like all three of you, but I have a bunch of people absent today, so just in case. And I won't say which student asked, but his name rhymes with Owen. And he was trying to ask if we make the plate infinitely big, even though the problem suggested the plates are infinitely big. We're going to make this one double infinity big. Would it act as a Faraday cage to block the electric field of the plate below? I'm not sure where to begin with my yes or no here because I'm not sure I know the answer. But
you can just move on if you want. This is.
Oh, I always want to, but I'm trying to answer your question. I don't know. Because I mean, it's not about the double infinities, although that's ridiculous. What if we had a finite plate and a plate that was much bigger than the finite plate? Would that suddenly overcome? Would there be an area right here? I think in reality there'd be an area right here with a weakened electric field, but I'm not sure it'd be zero. Okay. But there's so many other variables to take into account here. Are you talking about a plate on the top that is bigger and the surface density increases proportionately to cover that? If they're the same surface density, well, I don't think so, because that surface density would be spread out over a much bigger plate now. So I'm not sure it would act as a Faraday shield in that case. But like I said, there's too many weird variables there. If you're trying to anticipate like what I'm going to try and do on a test or something, or try to understand this better, this is the wrong direction.
Okay. Yeah. That was just theoretical. Not to my mind.
Well, all of this is a little bit theoretical, wouldn't you agree?
I mean, I did get something from that.
Excellent. So did I.
Thinking about Faraday cages too simplistically.
Okay, so let's go on to the next one because I'd like to do something else besides this today. The inner one is positive 2q, right? This is the two-sphere problem. Is that right? And the outer one is negative q, but the outer one is just a thin metal shield, right? Or a thin metal sphere, like so. And there's some geometry here. Sorry to bore you. R and 3R. And the outer one is the negative q, and the top one is the positive 2q. All right, good. Use Gauss's law and find the expression for the magnitude of the electric field. Now, you should know the answer without having to use Gauss's law. You should be able to write it down from memory. If you can't, I am disappointed. I've told you there's a few things to commit to memory. If you haven't committed it to memory yet, are you waiting for an invitation? So the electric field electric field is 0 for R less than R. It's inside a solid conducting sphere, a solid metal sphere. So there's no electric field inside. Now, for R between capital R and capital 3R, that's in this space here, you should be able to, without proof, write that that's got to be 2q over 4 pi epsilon naught r squared for this. Right? It acts like a point charge with charge 2q. So without proof, you should be able to do that. Bless you. Of course, writing that will not get you the points since they say in the problem, use Gauss's law. So you have to use Gauss's law. So put in a Gaussian surface. And if I were you, pay attention to all of these. We need 3 surfaces to do what the problem asks. Right? 1 for each R. If it says to use Gauss's law, then the very first thing you must write, Gauss's law. Don't shy away from it. Be clear and obvious. So for the first one, where R is less than the radius of the big sphere, and of course, I don't think I have to say this, but bigger than 0, Q enclosed is 0. That's not your answer, though. Make sure you do both sides of this. The right side of this isn't going to change for any of these. The right side of this will stay the same. R just keeps getting bigger. But put it in there. Let your test grader know that you understand that. Now, is there any part on the right side of this relationship that I need to go over? If so, let me know. I'll talk. Okay, so we're all good with that? All right, so you solve this for E and say that it's 0 in the first case. Then you move on. So for situations which R is between 3R and R, to solve it again, 2Q is the Q enclosed. And that's got to equal epsilon naught E 4 pi R squared. Solve it for E and get your 1 over 4 pi epsilon naught times 2Q over R squared. And then for R greater than 3R, still the same, still start with the same thing, except be careful about your U enclosed. This side is still E 4 pi R squared. That hasn't changed, right? It's still just a bigger and bigger surface. And in each case, this was R, then this was R, then this was R, right? All 3 cases. The difference is Q enclosed is just Q now, right? Because we are enclosing positive 2Q and minus Q, so the whole thing is just Q. So our electric field will be 1 over 4 pi epsilon naught times Q divided by R squared. Those are the 3 different expressions for the electric field. Any question about that? We all good? All right. Sketch a graph of the electric field as a function of R and distinguish on the graph the location of R and 3R. Now, on the AP exam, they are going to give you something that's going to look like this. And be prepared. This one wasn't much, but if the outer shell was like negative 4Q, that would have a distinctly different look to it, right? So let's take a look at this problem and then consider what would happen if the outer charge had enough charge to reverse the electric field. So electric field and R, I'm going to set up capital R and 3R. So we know the electric field is 0 here. And looking at these two expressions, we know we're going to have a discontinuity at 3R. In fact, at 3R, really there should be like a little bubble at 3R to indicate that there's no electric field at 3R because you're inside the shell of the metallic surface. They won't be very critical about that though, so I wouldn't worry about the little circle. Here's what I would worry about. You don't have really a starting point. You could put, and I would consider it, something like this. To indicate your starting place. Right, this is just outside of the sphere. Do you understand what I'm saying? We're just outside the sphere, so R equals capital R. It decays as 1 over R squared. Just make yourself a little swoop that decays. You can't easily know the difference between what 1 over R would look like and 1 over 2R would look like, and you don't have to. You just have to show that it's a clear inverse decay, or I'm sorry, inverse square, and that's good enough. But note that at this point, it's halved. So make it clearly in half and then continue. They're not going to care if you get the shape perfect. They just want you to see that it's decaying. But make sure at that point that you get half of the electric field there because you have clear evidence that the electric field is reduced by a factor of 2. Everybody follow along? You could go further and mark these 2 places over here. Generally, it's not necessary unless they specifically say to label the graph with the size of the electric field. But you could. Right? One's just going to be 2Q over 3R cubed. The other one's going to be Q over 3R cubed. If, instead, the outer one, say, had minus 3Q, then that would mean that my Q enclosed here would be negative. Right? Negative Q. And that would mean my electric field would be suddenly negative on the outside of that sphere. You would have to show that it is negative on the outside of that sphere. So suddenly, well, those letters are in the way, so you'll have to keep them in your imagination. There's 3R. Right, the electric field would suddenly inverse, be in the opposite direction, be on the negative side, but still getting smaller as it goes to 0. Everybody follow okay? So don't be worried. Electric field can be in either direction. So if suddenly a charge is negative, the direction of your electric field is inverting. All right. I want to answer the last question. This is a mess, though. See if we can kind of clean it up, maybe. All right, so the outside's negative Q, the inside's positive Q. We connect a wire between them. What do you think's gonna have to happen here? Yes, sir?
The free molecules will travel through the wire and then meet, and I would assume that they would become a charge of positive.
How many of you agree with what he had to state? Any counter alternatives? Go ahead.
When you like add up the charges, and then you have to like divide, I have to divide by 2, right? I got Q over 2.
2 over what?
Q over 2.
So the total charge of the system would be Q over 2?
It's like the distribution of a charge.
So what it says, what would the final distribution of charges if the spheres were joined by a conducting wire? So there are some things here I want you to think about. What drives the charges to be moved? What do you think pushes them around?
Moods on. Them repelling each other.
Okay, that's I think a good starting point. We have a collection of positive charges on the inner sphere, and they're trying to repel each other, and we have negative charges on the outer sphere. So they're attracting the positive charge. The real question is how much charge is going to move until they stop moving completely. Now, it would be nice to say they're going to do that when they're equal. The problem here is that that might not be true in this circumstance, because we have this inner sphere and outer sphere driving this. So the thing that's going to move the charges has still got to be a pressure due to an electric field. And we have two kind of competing arguments here between folks in the class. One is that we'll just sum it out, and the total is going to be whatever the net is, which is positive Q. But it's saying, what would be the final distribution of charge if the spheres were joined by a conducting wire? It's asking where the charges are going to go. The net charge isn't going to change, right? It's an isolated system. The net charge is still positive Q. Gauss's law suggests that you're going to have a distribution of charge that's going to reflect positive Q. Now, what I mean by that is, if you're at a place right here, and you connect this wire, which allows those charges to flow, will a point out here see any change in the electric field? Has the total charge changed in the system? Are you guys following this or not? Total charge is the same, so the distribution of charge has got to be that positive Q is spread on this surface. That has to be the result in order to maintain Gauss's law. So the electric field in here is certainly going to change. But anything on the outside, we'll see no difference because the net enclosed charge didn't change. So yeah, we'll get a distribution of positive charge on the outside of that shell to preserve the electric field outside the system.